These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. So let me start by asking you a question that might seem kind of weird. What is the most important factor in organic chemistry? What is the most important factor in organic chemistry? That's kind of a weird question, so maybe I'll just tell you what I think the answer to that question is. The most important factor in organic chemistry is the charges.
Oh.
And this is something, I don't know if that was what you were going to answer, but that unfortunately is something a lot of people don't really understand from their course. The most important factor in organic chemistry is the charges, and we're just going to keep emphasizing that over and over and over. So what we want to do in OChem as much as possible is improve our understanding, because the more we understand, the less we have to memorize. The wrong approach that a lot of people take to OChem is they think they're supposed to memorize every single detail of every single reaction, and that just becomes overwhelming and it's impossible to remember it all. In fact, we're supposed to understand as much as we can about the reactions, and the more you understand, the less you have to memorize. And if you did forget something, you can figure it out again. Well, what's the most important factor for understanding stuff in organic chemistry and figuring stuff out? The charges. So that's what we want to focus on first. So, to review, what is the most important factor in organic chemistry?
The charges.
That's right. So, if we want to predict what's going to happen in a reaction, what's the most important factor to consider?
The charges?
That's what I was going for. Yes, the charges. Now, if you want to explain why something happened in a reaction, what's the most important factor to consider?
I'd guess the charges.
That's the answer I was going for. Yes. Let's say that something doesn't happen in a reaction. If something doesn't happen in a reaction, what's the most important factor to use to try to explain that?
Probably the charges.
That's right. All right. Why am I asking the same question over and over? Well, I just want to reinforce this idea that we always go first to thinking about the charges, and we'll just keep coming back to that over and over. It's easy to say that, but it's hard for students to remember that for particular examples. Okay. Now, what does that mean? What does nature want? Does nature want charges to be big or small?
Small, neutralize them.
That's right. Or let me put it this way, does nature like charges?
Not necessarily.
So let's see. Does nature like or dislike charges?
Dislike.
That's right. Nature dislikes charges. You already mentioned, does nature prefer things to be charged or neutral?
Neutral.
Neutral, as you already said. Now, of course, nature is not a person, but oftentimes in science it helps to personify nature and pretend that there's things it wants. It just makes it easier sometimes to remember and understand the material. So I'll keep talking that way. All right, so we could say, kind of metaphorically, nature dislikes charges. Nature wants things to be neutral. So again, does nature prefer charges to be big or small?
Small.
Small, that's right. So how do you predict what's going to happen in a reaction? Well, is nature going to try to make the charges big or small?
Small.
Is nature going to try to make things charged or neutral?
Neutral.
Okay. One other point, is it better for a charge to be concentrated in one place or spread out?
Spread out.
Yeah, nature prefers charges to be spread out, because then there's less charge in any one place. So that's another way to make a charge smaller, to spread it out. Okay? All right, so we'll keep coming back to that idea of how important the charges are. Okay, so the first topic that I'd like to talk about is how to use this type of arrow, which hopefully you remember having seen from the first semester OChem courses.
Yeah.
Do you remember what the name of this type of arrow is?
Something like electron moving arrow.
That's right. Now they're called an electron pushing arrow.
Pushing, okay.
although intuitively it's could just as well be called electron moving. So it's an electron pushing arrow.
Okay.
Another name that's sometimes used is they're called curved arrows.
Okay. Makes sense.
Yeah, that's a logical name because they generally are drawn as being curved. But I think electron pushing is maybe a clearer name for that.
Yeah, a little more descriptive.
Yep. Okay. So this is the most important tool in organic chemistry. So that's what I wanted to start with. The most important tool in organic chemistry are the electron pushing arrows. So our most important first job is to make sure we understand the rules for electron pushing arrows. Now, you might not realize it, but every electron pushing arrow has exactly two parts. There are exactly two parts to every electron pushing arrow. There's a head and a tail. So the way to think clearly about electron pushing arrows is to think about which is the head and which is the tail. So which part is this part of the arrow?
The tail.
And how about this?
The head.
All right, so how about this part?
The head.
And this?
The tail.
And this?
Head.
And this?
And tail.
Okay, that's pretty easy. Often, so we're going to be using those terms over and over during the tutoring. I'm constantly going to be asking you, what's at the head? What's at the tail? Where's the tail? Where's the head? I find that even if students know those terms, sometimes they get confused in the middle of the problem and start mixing them up. So we want to try not to do that and be very careful not to mix up the head and the tail of the arrow. Now, what does the electron pushing arrow mean? Well, the electron pushing arrow, there's a couple of different ways to interpret electron pushing arrows. So here's the first way to interpret electron pushing arrows. The first and most obvious way is it shows something moving. Well, the electron pushing arrow shows the movement of what?
Electrons.
That's right. That's why you could call it an electron pushing arrow or an electron moving arrow. It shows that so the electrons are moving from where to where?
From the tail to the head.
That's right. Not from the head to the tail. They're moving from the atom. So to be more specific, the electrons are moving from the atom at the tail to the atom at the head. The electrons are moving from the atom at the tail to the atom, towards the atom at the head. Good. So that's what so they show the movement of electrons. So these do not show movements of atoms. These do not mean atoms are moving in any particular direction. They show the movement of the electrons. They're not atom pushing arrows, they're electron pushing arrows. Okay? So the electrons move from the atom at the tail to the atom at the head. For example, this arrow shows electrons moving from what atom to what atom?
Right there, it looks like it's moving from the oxygen to the carbon number 5, it looks like.
Good. That's good that you use those numbers. Now, this is a little bit subtle. Does that mean that this oxygen is completely losing the electrons? Well, no, because if you remember, there's 3 different kind of statuses you could have with electrons. You could own electrons, or you could share electrons, or you could completely lack electrons. So, for example, if you have a lone pair, you own those electrons. You're not sharing them with anybody else. So the oxygen owns this lone pair. But what about the pair? Do you remember that every covalent bond is really a pair of electrons? Every covalent bond is really a pair of electrons. Does the oxygen own the electrons in this bond? Well, I would say it doesn't own those electrons, it's sharing those electrons. So that's what I mean by the difference between owning and sharing. If electrons are in a bond, you're sharing them. And if electrons are in a lone pair, you're owning them. What about these electrons? Does the oxygen own, share, or lack these electrons? Well, I would say the oxygen just completely lacks those electrons because it doesn't have any ownership or sharing in those electrons. Those are shared between 2 other atoms. So that's what I mean by these terms owning, sharing, and lacking. So notice, just because the opposite of lacking is not necessarily owning, you could also share electrons.
Okay, yeah.
Okay.
Makes sense.
So the electrons in this lone pair, the oxygen owns them. And those electrons are moving towards carbon 5. Does that mean that the oxygen is going to completely lose the electrons? Well, no, it turns out instead what's going to happen is that the electrons are going to change from being owned by the oxygen to being shared between the oxygen and carbon 5. Okay. So The electrons here are moving away from what atom? The electrons are moving away from what atom?
Oxygen.
But notice it's a little bit subtle. That doesn't mean the oxygen is completely losing them. Even they're only moving partially away. Even though they're moving away, they're only moving one step away. They're moving from owning to sharing.
Sharing. Yeah.
And if they moved another step, then they would move from sharing to lacking. But so they're just moving from owning to sharing in this case. So the oxygen will have less possession of the electrons, but it will still have some possession of the electrons.
Okay.
All right, and how are the electrons moving for carbon-5? Well, would you agree previously carbon-5 completely lacked this lone pair? And this arrow shows that carbon-5 is going to start sharing the electrons.
Right.
So the point is you can only move one step at a time in this little table. It's impossible to go all the way from here to here. You can't go all the way from lacking to owning in one step. That's just one of the rules for organic chemistry. One of the rules for organic chemistry is you can never go all the way from lacking to owning. That never happens. And you can never go all the way from owning to lacking. That never happens. You can only go one step at a time. You can go from owning to sharing, or sharing to lacking, or lacking to sharing, or sharing to owning. Those are the possibilities. But you can't go from owning to lacking or lacking to owning. That's just one of the rules that students sometimes are not familiar with.
Yeah, that's a good way to look at it.
Okay, so what's happening here with carbon-5? It's going from lacking to sharing. Now what about this arrow? This arrow shows the electrons moving from where to where?
It looks like they're moving from the shared stance between carbon-5 and oxygen to the owning of the oxygen.
Excellent, good. So this arrow is a little bit different. We could say that the arrow is starting on what we call this pi bond. The arrow is starting on this pi bond. And that pi bond, as you said, was being shared between the oxygen and carbon-5. And it looks like carbon-5 is losing those electrons completely. Carbon-5 is going from sharing those electrons to lacking them. And the oxygen here is going from sharing the electrons to owning them. I think that's what you said. So good.
Yeah, that
All
makes
right.
sense.
So that's the meaning. So it's really important to understand the meaning of those electron-pushing arrows. Okay, good. So that's what we mean when we say that the electron-pushing arrows show the movement of electrons. Electron-pushing arrows show the movement of electrons. The atom at the tail is, the electrons move away from the atom at the tail and towards the atom at the head. But just because you're moving away from the atom at the tail doesn't mean that the atom at the tail is completely losing the electrons. Instead, they might be going from owning to sharing, or from sharing to lacking. Okay, so that's the meaning of our these types of electron-pushing arrows. Let's see.
Okay.
Okay. What's the most important? So the next thing we want to do is learn how to draw the product based on the electron-pushing arrows. If you're given electron-pushing arrows, you should be able to draw the product based on those electron-pushing arrows, because there are rules for drawing the product based on the electron-pushing arrows.
Okay.
There's rules for drawing the product based on the electron-pushing arrows. So that's the most important topic for us to start with, because almost every single problem in the course is going to involve electron-pushing arrows, and we need to know the rules for drawing the product based on those electron-pushing arrows. I think a lot of students don't realize that there's rules for the arrows. They think they're supposed to kind of figure stuff out from the arrows, but there's really mechanical rules. So our job here is just to learn the rules. You can't play chess if you don't know the rules for chess. You can't play soccer if you don't know the rules for soccer. There's specific rules for using electron-pushing arrows, and we just have to learn those specific rules. Okay, so the first rule, again, do you remember what's the most important factor in organic chemistry?
The charges.
So the most important rule that the electron-pushing arrows have is they tell you how to change the charges. Electron-pushing arrows tell us how to change the charges. So we need to focus on that. How do they tell us how to change the charges? So let me give you an example. So I'm going to start without, I'm not going to be giving you a full reaction or full molecules or even actual atoms. I'm just going to give you a part of a reaction so we can focus just on the rules. So I'm going to make up an atom, just call it A, just as a placeholder. And this is obviously only part of the reaction because I didn't show you who's at the head of this arrow. But I just want to focus on this one part of the rules here. So now it turns out that the electron-pushing arrows are, what type of charges do they affect? The electron-pushing arrows affect what are called the formal charges. What's the formal charge on atom A here?
-1.
Yeah, that should have been an easy question because I'd already drawn it in for you. Good. Although notice when we say negative, as you said, what we really mean is -1. When we say negative, what we mean is -1. Okay, so the question is, what is going to be the charge on atom A in the product? What is going to be the charge on atom A in the product? Well, it turns out that it's a very simple mechanical way to figure that out. You just have to ask yourself two questions. First, ask yourself, what formal charge is atom A starting with? So again, what formal charge does atom A start with in the starting materials here?
-1.
That's right. And then you ask yourself, is atom A gaining or losing electrons?
Losing.
Okay, so if you start with -1 and you lose electrons, we should be able to mechanically figure out the new charge on atom A. The rule is, if you're losing electrons, you just become one step less negative. And if you're gaining electrons, you become one step more negative. That's just a mechanical rule that always works for electron-pushing arrows. If the atom is losing electrons, it always becomes one step less negative. And if the atom is gaining electrons, it always becomes one step more negative.
Okay.
So, for example, in this case, if we were losing electrons, since we started with a charge of -1 and we're losing electrons, if we become one step less negative, we'd become neutral. So I'll show that in the product here, A is now neutral. So there's no symbol for neutral, but I just won't draw any charge. If we don't draw any charge, we've shown that it's become neutral. So that would be the rule for interpreting this electron-pushing arrow. We've gone from negative to neutral. Does that make sense so far?
Yeah, it does.
So let's do a different example. Here's a different example. So let's go through the same two-step process. What formal charge did this atom start with?
It looks like it does not have a negative sign, so it looks like it does not have a formal charge.
That's right. Maybe that's kind of a weird question, but how do you tell what formal charge things start with? Well, we'll go into that in more detail later, but fortunately in organic chemistry, if there is a formal charge in the problem, it'll usually already have been drawn for you. In organic chemistry, usually if there's already a formal charge, it'll usually already have been drawn for you, although we'll talk more about that later. So since I didn't draw any formal charge, it's safe here to assume there is no formal charge to start with. So you figured that out correctly. There was no formal charge to start with. So to review, what formal charge does this atom start with?
0.
And is it gaining or losing electrons?
Losing.
So what should be its charge in the product?
A +1.
It's just that simple. So that's a very simple rule for drawing the product based on the electron-pushing arrows. What's the most important factor in organic chemistry? The charges. And the arrows make it easy to figure out the new charge. The arrows are supposed to make it easy to figure out the new charge. So if we follow that, that should be easy. Okay, good. So let me write down the two-step process here that you ask yourself. Okay, so let's see. We're writing down how to figure out the new charge based on the electron. Pushing arrows. You just ask A formal charge did the atom start with? I should say this is a method for figuring out formal charges.
Okay.
And then you ask, is the atom gaining or losing electrons? Do you see it should be obvious whether you're gaining or losing electrons because you can easily figure that out from the electron-pushing arrows. The electron-pushing arrow should make it obvious whether the atom is gaining or losing electrons. You just need to be in the habit of always asking yourself these two questions. We always ask ourselves these two questions, and that should make it easy to, and then if the atom is gaining electrons, it becomes one step more negative, and if it's losing electrons, it becomes one step less negative. Okay.
Okay.
All right. I can't see what you're writing now, so you'll have to tell me when you're ready. Do you have that in your notes?
Yeah, I'm ready to go.
Okay, that's fine. Sometimes I'll have to ask you that. If we were in the same room, I could see when you're done writing and when you've looked up at me again. But since I can't see you right now, you'll just sometimes I'll just have to ask you whether you're done taking notes. Okay, so let's try that process here. What would be the new charge on this atom when this reaction is over?
A negative charge, -1.
Let's see. What formal charge did this atom start with?
0.
And is it gaining or losing electrons?
Gaining.
So you're right. It becomes negative. It's just that simple. Good. And what formal charge will this atom get?
0.
Because what charge did it start with?
A positive charge, +1.
Right. And is it gaining or losing electrons?
It gained electrons.
So it became one step less negative. Okay. One step more negative, I should say. Okay. These are the only 4 patterns in organic chemistry for the charges. These are the only 4 patterns that we're going to see. So the point here is notice that this is a straightforward mechanical method for figuring out the charges. Notice you don't need to count the lone pairs or the bonds to figure out formal charges, usually in organic chemistry. So when you took your general chemistry course, I don't know if you remember, maybe it's been a while, but when you took a general chemistry course, you learned how to figure out formal charges by counting lone pairs and counting bonds. But notice that would have been impossible here because I didn't show you the lone pairs or the bonds on this atom, but you don't need that in organic chemistry. Because usually the formal charge on the starting material will already be drawn for you, and you can figure out the new formal charge just using the arrows. So we don't usually have to count bonds and lone pairs to figure out formal charges in organic chemistry. That would be overcomplicating things. Okay, good. All right, so what can we say here? Which atom's charge is changing?
The B atom.
What will be its new charge?
It will be 0.
That's right. What about A? What will be A's charge in the product?
The same, 0.
That's right. How do you know? How do we know that A's charge is not changing? Well, because there's no arrow telling us to change its charge. This is a very important principle in organic chemistry that a lot of students don't recognize. The only changes that you're allowed to make are the changes that the arrows tell us to make. We have to make all the changes the arrows tell us to make, but also very important, we should not change anything that the arrows don't tell us to change. It's very important not to change anything that the arrows don't tell us to change. So since this arrow did not tell us to charge the change on A, we can't change the charge on A. All right, good. So whose charge should I change here?
C.
And what's its new charge?
Looks like it'll have a negative charge. Or a positive, sorry.
Which one? Positive or negative?
Positive, it's losing electrons.
Yes, good. So you did something that was very important there. You double-checked yourself. That might seem obvious, but it's surprising how often students don't do that. It's surprising how often students will just say something and then hope for the best and hope that it's correct. So it's very good there that on that problem you actually checked your answer. That's crucial, because what's the most important factor in organic chemistry?
The charges.
So does it matter whether we label this as positive or negative?
Definitely.
Yeah, it's the most important thing. It's the most important thing. If we get this wrong, the problem will be impossible to complete after that. So you can see, it's easy to make mistakes on these problems. It's like math. Most people know how to do, say, long multiplication, but does that mean most people know how to do, say, long multiplication? But does that mean they never make a mistake when they do long multiplication? Well, people often make mistakes if they don't double check themselves. I think you already know how to use the rules for changing the charges here, but does that mean you're never going to make a mistake? Well, probably you will make mistakes sometimes. It's important to double check yourself. Okay, so the arrows here show us that this is actually losing electrons, so it's good that you took your time and checked yourself. Again, you have to treat this like math and double check your answer for each step. So that's good that you did that. Okay.
Thanks.
So what would be the new charges for this molecule?
It would, the atom D would have a 0 charge if it's gaining electrons.
And what happens to the charge on B?
It's unaffected.
And C?
The same. It would not be changed.
And how do you know they're not changing?
There's no arrows
Telling us to change their charges. Yes, we only do what the arrows tell us to do. Okay, good. All right, now I think I'm going to ask you a couple weird questions. So we'll get ready for some weird questions. Here's a question.
Okay.
What would be the new charge on atom A after this step?
It looks like it would have a positive 2.
That's right, it would.
2 plus, I guess. Yeah.
That's right. How do you know?
Well, it's already at a positive 1, and then we lost electrons, so it moves 1 step in the positive direction.
Okay, that's right. Excellent. Do you see why I said this was weird? Well, if you remember from the first semester, this never actually happens in OChem. I don't know if you remember from the first semester, you never actually saw an example where something had a +2 charge. Because does nature like charges?
No.
No. Does nature want charges to be big or small?
Small.
Right. So nature is never going to allow anything in organic chemistry to build up a +2 charge. Now, if nature had its way, everything would always be neutral. But you don't always get everything the way you want. Nature can't keep everything neutral. Sometimes things get positive or negatively charged, but they never get more than a +1 or a -1. We never go up to +2 or -2. So I'm going to make a note. This never happens in OChem. I guess it would be better to say it never happens in an introductory organic chemistry course. I'm sure there's probably some weird examples in real life where something actually gets a +2 charge in organic chemistry, but we're focusing on what's going to happen in the reactions you're going to see in your course. So in an introductory OChem course, this never happens. So I'll just summarize: this never happens in an introductory OChem course. Okay. So what does it mean then? What does this mean if we got a +2 charge? What that means is, would you agree this means we drew a bad arrow?
It would in OChem.
Yeah, this means we must have drawn a bad arrow. Because after all, in organic chemistry, you're not usually really given the electron-pushing arrows, right? In organic chemistry, you have to draw the arrows. I've been drawing the arrows for you in all the previous problems because we're just introducing the material, but ultimately you have to learn how to draw the arrows yourself. So how do you know? You have to decide whether you've drawn reasonable arrows or unreasonable arrows. So would we say this is a reasonable electron-pushing arrow or an unreasonable electron-pushing arrow?
Unreasonable.
That means we've made a mistake and we shouldn't have drawn it. Okay. So if you ever draw an electron-pushing arrow that creates a positive 2 charge, you shouldn't ignore that. You should say, I need to go back and change my arrow. Now, oftentimes, unfortunately, what would tend to happen here is oftentimes people are kind of on autopilot, and oftentimes people here might just say, oh, this is now going to be neutral. They don't think clearly what's going to happen here because they don't expect to see the positive 2 charge. So you have to be open to the possibility that your arrow could give you a positive 2 charge, because that's the way you can see that you've drawn an unreasonable arrow. So this would be an unreasonable arrow.
Okay.
All right.
Yeah.
So what we're doing here is we're starting to see the more important skill of how you can decide what are good electron-pushing arrows to draw. This might seem obvious, but I can't tell you how many times I've seen people, when I let people draw the electron-pushing arrows, they draw arrows like this all the time. So hopefully it seems obvious that this is unreasonable, but in real life it's actually not obvious to people. Very often students draw arrows like this, even though it makes absolutely no sense. All right?
Okay.
So what would be the new charge on this atom after the reaction?
A -2 charge.
That's right. So does this seem like a reasonable or an unreasonable electron-pushing arrow?
It seems to be unreasonable.
So again, this would be an indication that we made a mistake.
Okay.
Okay, so what should you do if you end up with a positive 2 or a negative 2 charge? You should always say, I guess I made a mistake drawing my arrows, and you need to go back and draw better arrows. Anytime you get a positive 2 or a negative 2, that means you've made a mistake. It doesn't mean you made a mistake with the charges, it means you made a mistake with the arrows. And then you need to go back and change your arrows so you don't get a positive or a negative 2.
Okay.
All right, because so there's only 3 charges we should ever have in organic chemistry. What are the only 3 reasonable charges in organic chemistry?
A -1, 0, or +1.
That's right. So if your arrows give you a positive or a negative 2, that means you need to fix your arrows. All right, good.
Sounds good.
So the main thing we're focusing on right now is how to draw the product, given the electron-pushing arrows. But we just did a little short lesson on how to figure out the right arrows to draw. The first lesson in how to figure out the right arrows to draw is don't draw arrows that end up giving you positive 2 or negative 2 charges. Don't draw arrows that would give you a positive 2 or a negative 2 charge. That's always a mistake. All right?
All right.
Okay, so let's continue. We want to continue with the rules for changing the charges in organic chemistry. So here's the next very important rule. You should always change 2 charges on every step of every mechanism. You should always change 2 charges. That's so important, I'm going to write it down.
Okay.
Change 2 charges on every step of every mechanism. We always, or almost always, change 2 charges on every step of every mechanism. Or to be more specific, you change the charge on 2 atoms. Change the charge on 2 atoms on every step of every mechanism. So the next question you should be asking yourself is, how do I know which 2 charges to change? How do we know which 2 charges to change? We're only going to change 2 charges, but there's going to be lots of charges. There's going to be lots of atoms. Well, the answer is you change the charges at the beginning and the end of the string of arrows. Okay, so here's an example that we can use to try to work on this. Now notice again, this is kind of a made up fake example. I'm not using real atoms here. I'm using made up letters, A, B, C, D, and F, because I want to emphasize we're not supposed to be relying on our memory of the reaction to figure out what to do. Even if you've never seen the reaction before, even if it's a fake made up reaction like this, the arrows tell us what to do. So we're going to change two charges here. Which two atoms are we going to change the charges on? Well, remember we want to change the charges on the atoms at the beginning and the end of the chain of arrows. So here's what I mean by that. I would say that A is at the beginning of the arrows. And I would say that E is at the end of the arrows. Do you see how I would say that?
Yeah.
Okay. On the other hand, how about D? Is D at the beginning and the end of the chain of arrows? No, I would say that D is in the middle of the chain of arrows. Because D is at the head of one of the arrows, but it's at the tail of another arrow. So we only change the charges at the beginning and the end of the chain of arrows. We don't change the charge on every single atom that's in the middle. So we only change the charges on A and E here. Okay, so what will be the new charges? What's going to be the new charge on A?
0.
That's right. And what's going to be the new charge on E?
-1.
That's right. And what's going to be the new charge on D?
It'll be the same. It'll be 0.
It's not changing because it's not one of the two atoms whose charges we're changing. That's right. What'll be the new charge on C?
0. It'll be this no change.
That's right. So only A and E are changing. All right, I'm not going to bother drawing the bonds and the product yet because I don't want to talk about that yet. I want to start by just focusing on the charges. So we'll talk about the bonds later. For now, we'll just say that the only two charges we're changing are A and E. And we won't worry about what the bonding would be in the product. We'll just focus on that. Okay, good. So who are the two atoms whose charges we're changing?
E and B.
What will be their new charges?
E will have a 0 charge, and B will have a negative charge.
Excellent. Great. Who are the two atoms whose charges change here?
C and E.
And their new charges will be?
C will have a positive charge, and E will have a negative charge.
Excellent. What would be the new charge on A?
It will not change. It'll still be 0.
How do you know?
No arrows tell us to change the charge.
Excellent. Good. And what will be the new charge on D?
D has no change either. He's in the middle of the chain of arrows.
Good. Notice that's a little bit more subtle than A. It's obvious that A is not changing because there's no arrows involving it. D is a little bit trickier because there's a bunch of arrows that involve D, so it wouldn't be surprising if something about it changed. But because it's in the middle of the arrows, its charge is not changing. By the way, can you see why it's logical not to change the charge on D? So going back to C, is C gaining or losing electrons?
It is losing electrons.
Because it's at the tail, so that's why its charge changed. And is E gaining or losing electrons?
Gaining.
Because it's at the head. But how about D? Why is its charge not changing? Well, it's because, do you see, it's gaining electrons from this head, but losing electrons from the tail. Those two things are going to cancel each other out, so overall its charge hasn't changed. That's why it should make sense that any atom that's in the middle of the arrows, its charge will not change. If you think about it, any atom that's in the middle of the chain of arrows will always be, what does it mean if you're in the middle of the arrows? If you're in the middle of the arrows, that means you're at the head of one arrow and the tail of the other. So that means that you're going to be gaining electrons from a head and losing electrons from a tail, and those two things will always cancel out. So overall, the charge won't change. Okay, good.
Okay.
Now notice how this is a little bit subtle here. So again, was C gaining or losing electrons?
Losing.
That's why it went from neutral to positive. Now notice it's a little bit subtle. Does that mean that C is going to completely lose these electrons? Well, if you remember our earlier discussion, that's not what's going to happen. In this picture, C owns this lone pair. And in the product, it's going to be sharing the pair with D. I haven't drawn it, but it's going to be forming a bond with D. So C is not completely losing these electrons. It's actually going to go from owning them to sharing them. But it turns out that that's enough to change the formal charge by one step. Anytime you go from owning to sharing, that changes your formal charge by one step. And if you go from sharing to lacking, that would change your formal charge by one step. And if you go from lacking to sharing, that would change your formal charge by one step. And if you go from sharing to owning, that would change your formal charge by one step. So it's even though the arrows don't always show, even though the arrow doesn't show C completely losing the electrons, it's still going to lose enough electron density to change the charge by one step. Well, the good news is we don't really have to think about that for every single problem. We can just trust the rules. We can trust that the rules are going to work. Okay, good.
Good.
How many charges should we change on every step of every mechanism?
You should change 2 charges on every step.
That's right. So which 2 atoms' charges will we change here?
C and D.
And what will be their new charges?
C will lose electrons since it's at the tail of the electron-pushing arrow, so it will go from a neutral or 0 charge to a positive charge.
Good.
And then D, because it's at the head of the electron-pushing arrow, will go from a positive charge to a neutral or 0 charge.
Excellent. Perfect. So that was the right answer, and that was also a good explanation of that. So that's the right way to think about that. Good. Okay, which atoms' charges will change here?
B and F, or E, sorry. B and E.
And what will their new charges be?
B will have a positive charge, and E will have a negative charge.
Good. And again, it's good that you double-checked yourself. At first you were thinking F, but then you checked that and went and changed E. So that's important. Everyone makes mistakes. The important thing is to catch those mistakes. That's good. Notice this reaction is a little bit weirder than the previous ones. Do you see, this is what's called an intramolecular reaction. If you remember those, all the previous examples were reactions between 2 separate molecules. 2 separate molecules, but here there's only 1 molecule. Sometimes one part of a molecule can react with another part of the same molecule. Sometimes one part of a molecule can react with another part of the same molecule, but the good news is that that does not change the rules for electron-pushing arrows. The rules for the electron-pushing arrows stay the same, even though this was an intermolecular reaction and this is an intramolecular reaction. Okay? Do you see what I mean by intramolecular reaction?
Yeah, it's within the same molecule.
That's right. Okay. But the important point is it didn't make much difference. The rules for the electron-pushing arrows are the same either way. Okay. All right. So the main point here is that there's rules for electron-pushing arrows. You don't need to memorize what happens to the charges in each step. You can figure it out using the electron-pushing arrows. You can see that because obviously you didn't have these examples memorized because they're fake. These are not real molecules, but you were still able to figure out the right answers because of those rules. Good. Okay. So now we've learned that the electron pushing arrows tell us how to change the charges. To review one more time, how many charges do we change on every step of every mechanism?
2.
Yeah, we always need to make sure we've done that. But that's not the only thing the arrows tell us to do. The other thing the arrows tell us to do is they tell us which bonds to form and which bonds to break. The arrows also tell us which bonds to form and which bonds to break, and that's all there is to it. Those are the only things the arrows tell us to do. The arrows tell us which two charges to change, which bonds to form, and which bonds to break. So the next thing we have to go into is look at how they tell us whether to break or form a bond. So how can you tell if the arrow is telling you to form a bond? First of all, let's look at the different types of bonds. Do you remember the distinction between sigma and pi bonds?
Yeah, the sigma ones are the single line, and the pi bonds are a double line.
So what type of bond is this?
Sigma.
And this?
Also sigma.
And this?
That's another sigma bond.
And what type of bonds are these?
Pi bonds.
All right, it looks like you've somewhat misremembered that. Actually, when you have a double bond, one of them will be sigma and one will be pi.
Ah, thanks.
When you have a double bond, one of them is a sigma bond and one of them is a pi bond. Okay, now we'll just do a brief review of that right now, and maybe at another point we'll go into that in more detail. How about when you have a triple bond? When you have a triple bond, one of them is a sigma bond and the other two are pi.
Okay.
Which of these is the sigma and which is the pi? Well, it doesn't make any difference. If you wanted to, you could call the middle one the sigma and the two outer ones the pi. Or if you wanted to, you could call the bottom one the sigma and the two top ones the pi. The important thing is that a triple bond is one sigma bond and two pi. Okay, so let's make sure we review that a little bit. So what type of bonds do we have here?
There's one pi and one sigma bond.
And how about here?
That's a sigma bond.
And here?
A sigma.
And here?
Another sigma bond.
And here?
Two pi bonds and one sigma bond.
And here?
That's a sigma bond.
How about here?
That looks like one pi and one sigma bond.
Okay, good. All right, maybe at some point we'll go into more detail about sigma and pi bonds, but that's the review we need now. There's two different types of bonds in OChem, sigma and pi bonds. Okay, so how can you tell if you're going to break a bond? There's a very simple rule. It's a very simple rule. You break a bond whenever the tail of an arrow is on the bond. I think this is pretty intuitive. You break the bond whenever the tail of an arrow is on the bond. Tell me when you have that in your notes.
Yeah.
Okay.
I got that.
Now, the important point here is, suppose the tail of an arrow is not on a bond. Should we break that bond? And the answer is no. We only make the changes the arrows tell us to make. And this is really crucial. We only make the changes the arrows tell us to make. Very often, students will break a bond because it feels right. But we shouldn't break a bond because it feels right. We should only break a bond if there's a tail of an arrow telling us to break that bond. Okay.
Okay.
Does this arrow tell us to break a bond?
It does. That bond between atoms B and D.
Great. That's good. And that's good that you didn't just say you're going to break a bond, but you were specific and said which two atoms you were going to break the bond between. That's very important. So should we break the bond between A and B?
No,
No. Why not?
the arrow didn't say to.
Yeah, you only make the changes the arrows tell you to make. That's right. So here we would only break the bond between B and D. So it really is just that simple. Okay, very good. Does this arrow tell us to break a bond?
Yes, it does.
Between what two atoms?
Between the B and D atoms?
Good. So, how many bonds will there be between B and D in the product?
A single sigma bond.
Excellent, good. So something I didn't explain to you, but you just figured out on your own, you only break one bond at a time. So if you start with one bond, and it's at the tail, then you end up with no bonds between the atoms. But if you start with two bonds and you break it, then you would end up with one bond between the atoms. Good. So notice it doesn't really matter whether the bond is a sigma bond or a pi bond. The way that you show to break it is the same in both cases. Here we're breaking a sigma bond. Here we're breaking the pi bond. But the way we show it is the same in both cases. What you said was correct. Does this arrow tell us to break a bond?
No, it does not.
Okay, that's all there is to it. So we would not break any bonds based on this arrow. Because the tail of this arrow is not on a bond, it's on a lone pair. So we're not going to be breaking any bond based on that arrow. Does this arrow tell us to break a bond?
No, it does not.
How can you tell? How do you know?
The tail of the arrow is not on a bond. It is on a negative charge.
That's right. So it's a pretty simple rule. That's good. So the way you explained that was correct. Does this arrow tell us to break a bond?
Yes, it does, between the A and B atoms.
Now notice this is a little bit more complicated example because this is another intramolecular reaction. This would be another intramolecular reaction, but it doesn't really make any difference. I don't know if you even had to think about that. The rules for the arrows are the same for inter and intramolecular reactions, so we can still use the same rule. This tells us to break a bond. Okay, well that was a pretty simple rule, so I think we have that down. So the electron arrows tell you to break a covalent bond when the tail of the arrow is on the bond. By the way, notice here we're talking about covalent bonds. Those are the bonds that are indicated by dashes. Another type of bond is ionic. So we're not talking about ionic bonds right now. Maybe later we'll talk about ionic bonds, but here we're talking about covalent bonds. Those are the types of bonds that you indicate with a dash. All right?
Okay.
Well, we're almost done then with the rules for electron-pushing arrows. We've learned how to change the chart. We've learned how to know which charges to change, and we've learned how to know when to break a bond. So there's only one thing left. The only thing left is we have to know when to form bonds. Now this one is a little bit, unfortunately, a little bit more complicated than before. Not super complicated, but a little bit more complicated. So let me write this down. The arrows tell you to form a sigma bond when, this rule is a little bit more complicated, when the head of an arrow is on an atom. Here's the complicated part. That was not previously sharing the electrons. So we'll just write that down in our notes, and I'll give you some examples to show what that means. Tell me when you have that written down.
Okay.
So let me give you some examples. This part right here is the part that's a little bit confusing. All right, now first of all, does this arrow tell us to break a bond?
Yes.
Yeah. Which bond?
The sigma bond between A and B.
Yes. Now, does it tell us to form a bond? Well, the head, where is the head of this arrow?
It's on atom B.
Now, was B previously sharing the electrons that are represented by the arrow? Where are the electrons coming from in this arrow?
The previously shared bond between B and A.
Yeah, we're talking about these electrons. So would you say B was previously sharing those electrons or not sharing them?
Sharing them.
That means this is not an arrow that forms a bond. Remember, we only formed the bond when the atom was not sharing the electrons. So this arrow does not form a bond.
Okay.
It's kind of a double negative. Or, well, I don't know, a single negative. But anyway, because it was single negative, it was sharing the electrons, so we do not form a bond with this arrow.
Yeah, I don't think we have double negatives in OChem.
Yeah, okay. All right, now let's analyze this arrow. So first of all, does this arrow tell us to break a bond?
No, it does not.
Because the tail is not on a bond.
Right.
Good. Now we have to ask, should we form a bond? Well, which atom is the head of this arrow on? Which atom is the head of the arrow on?
F.
Now, where are the electrons coming from that are moving towards F? Was F previously sharing those electrons?
No.
No, it wasn't. By the way, maybe actually I haven't quite explained this. The arrows are coming from this negative charge, but what does this negative charge represent? This negative charge represents a lone pair on B. So where are the electrons coming from here? When electrons are coming from a negative charge, that means they're coming from a lone pair. That's the convention. These are really coming from a lone pair. So to review, was F previously sharing the electrons that are now moving towards it?
No.
Well, because it was not previously sharing the electrons, we do form a bond.
Okay.
So hopefully now that this makes more sense what I was saying here. You form a sigma bond when the head of the arrow is on an atom that was not previously sharing the electrons. Here F was not previously sharing the electrons that are moving towards it, so we do form a bond. Most of the rules we've gone over today I think were pretty simple. This one's a little bit subtle, but with a little practice it shouldn't be super complicated. Okay, so here's the situation here. So here's an example of an arrow where we do form a bond. Here's an example of an arrow where we do form a bond. So notice some arrows, like this one, break bonds, but don't form them. And some arrows, like this one, form bonds, but don't break them. Unfortunately, there's also some arrows that both break and form bonds. There's also some arrows that both break and form bonds. So you could break a bond, you could form a bond, or you could do both. You could break a bond, you could form a bond. Sometimes you do both. So does this arrow tell us to break a bond, form a bond, or both?
Just break a bond.
Between which two atoms?
E and F.
Good. By the way, did we remember to do that up here? Here we said we were forming a bond. We're forming a bond between which two atoms?
B and F.
B and F. The arrow should make that clear. Good. But we're not forming a bond here because F was previously sharing the electrons that are moving towards it. Good. Does this tell us to break a bond, form a bond, or both?
There's no bond being broken, but there is a bond being formed between E and G.
Perfect. That's right. How do we know to form a bond here? Because G did not previously share the electrons that are moving towards it. The electrons were just coming from that lone pair. Good. Does this arrow tell us to break a bond, form a bond, or both?
Just form a bond. It does not break a bond. It was coming from a lone pair. So the bond will be forming between atoms B and F.
Excellent. And does this tell us to break a bond, form a bond, or both?
It will break a bond, not form. It will break a pi bond that was between F, G, and G.
Good. Excellent. How did we know that this told us to form a bond? Because the electrons that are moving towards F were not previously shared by F. They were just a lone pair on B. But this does not form a bond because the electrons that are moving towards G were already being shared by G in the pi bond. Very good. So does this tell us to break a bond, form a bond, or both?
It tells us to form a bond that looks like it's forming a pi bond between A and B.
Yeah, I guess I got ahead of myself. We didn't talk about how to know when you're forming a pi bond. The way to form a pi bond is different from a sigma bond, so I guess I should have introduced that rule before, but it looks like you've already figured it out. So the rule is that we form a pi bond when the head is on a bond. So I'll go ahead and write down that rule.
Okay.
The arrows tell you to form a pi bond when the head of an arrow is on a bond. So notice it's easier to tell when you're forming a pi bond than a sigma bond. The rule for forming sigma bonds was a little bit subtle. The rule for forming sigma bonds was based on whether the head of the arrow was on an atom that was not previously sharing the electrons. That's a little bit of a subtle rule for forming sigma bonds. But the rule for forming pi bonds is very straightforward. You form a pi bond when the head of the arrow is on a bond. You already kind of figured that out without me even telling you the rule. So that's good. Okay, so how about this arrow? Does this arrow tell us to form a bond, break a bond, or both?
Looks like it's telling us to break the pi bond between B and D.
Good.
It does not look like it's forming, but well, it I guess is coming from electrons that were not previously shared by E, so I guess technically it would be creating a bond.
Okay, that part you had a little trouble with, but it's good that you kept thinking about it. It sounds like you might have changed your original answer. That's very important. It's crucial to know whether it's forming a bond, right? You know, you eventually ended up with the right answer. This is forming a bond. and you figure that out correctly, it's good that you applied the rules we were talking about. The head of this arrow is on E. Well, E was not previously sharing the electrons that are moving towards it. Previously, the electrons that are moving towards E were in this pi bond. So that's the situation when we're also forming a bond. So this is the first time we've seen an arrow that both broke a bond and formed a bond.
Okay. Could I ask a question about that?
Yeah, go ahead.
Because those were equally shared between B and D, where would the bond be formed?
So are you asking? So are you asking like which two atoms it's going to be formed between? So there seems like two possibilities. It might be formed between B and E or D and E. Well,
Right.
here's how to figure it out. Remember, nature does nature want to prevent or form charges?
Prevent.
So think about B. Think about this arrow. Is this arrow moving electrons towards B or away from B?
Towards.
So would that tend to increase or decrease B's charge?
Increase.
Does nature want the charge to increase?
No.
So this arrow should be interpreted in a way that prevents the charge from being formed. So what basically here, who should be losing the electrons from this tail? Technically, this arrow is ambiguous. We can't tell whether B is losing the electrons or D is losing the electrons. But we can use our knowledge of how nature deals with charges to figure this out. So who needs to lose electrons here, B or D?
B.
Because it's gaining electrons from this arrow, and we want to cancel that out. So would you agree if B is losing the electrons in the bond, it can't be forming a new bond, because they wouldn't actually lose those electrons. So who's going to form the new bond? D and E. D and E will form the bond because that way B will both be gaining electrons and losing electrons. So that's good that you were thinking about that. That's a very important point. That's one of the more subtle things we've looked at so far. So it's true that when the tail is between two atoms, it might seem a little ambiguous. This tail seems ambiguous as to who's going to form the bond, but we can really figure it out.
Okay.
Basically, it's actually a pretty simple rule. If an atom is gaining a bond, it also wants to lose a bond in order to stay neutral. So since B is gaining the bond with A, it's also going to want to lose the bond with D. And it's not going to want to replace that with a new bond with E, because then it wouldn't really be both gaining and losing a bond on net. Okay, so this tells us to both break a bond and form a bond. Which two atoms here will be forming the bond?
Between D and E.
That's what we were just talking about. Yes.
Yeah.
Not between B and E. So that was another subtle point, but that's very important. So we'll practice that more as we go along. Okay, and then how about this arrow? Does this tell us to break or form a bond?
Only to break, because the electrons were formerly shared with the atom that is now receiving the electrons.
F. That's right. Good. So this example here now shows us all three possible types of arrows. So now we're getting into more complicated examples. Here's an arrow that tells you to form a bond. Here's an arrow that tells you to break a bond. But here's an arrow that tells you to both break and form a bond. Okay. So that's a very important example right there. Very good. Okay. Does this tell us to break a bond or to form a bond?
This looks like it is forming a bond. It will not break a bond.
Form a bond between which two atoms?
D and E.
And how about this arrow?
It looks like it will form a bond and break a bond.
Who is it going to break the bond between?
E and F.
Because that's obvious because the tail is on a bond. And who's it going to form a bond between?
F and G.
This is an easy case because it's forming a pi bond. That's easy to see. Okay, good.
Okay.
So what does this arrow tell us to do?
That is going to form a bond between B and E. Will not break a bond.
Great. And how about this one?
That will be both breaking a bond and forming a bond. It'll break the pi bond between E and F, and it'll form a pi bond between F and G.
Perfect. Shortly before today's session, I sent you an email with a handout. Did you get that email?
Oh, you know what? Don't have that with me right now. Let me pull that up. Sorry.
That's okay.
Okay, I've got it.
Excellent. Very good. All right, and I'll put it up on my screen as well, but you can follow along on the paper. So let's move to page 2. Do you see at the top of page 2 is what we've been talking about, right? The rules for using electron-pushing arrows to draw the products of a step. Yeah, is that in your printout?
Mm-hmm. Yeah,
Okay,
that's good.
so we've just summarized those rules. So every electron-pushing arrow, if the arrow is breaking a bond, you erase the bond. If it's forming a bond, you draw that bond. And if it's both breaking and forming a bond, you erase the bond that breaks and draw the bond that forms. Pretty obvious. By the way, down here, how do you know whether to break a bond, form a bond, or both? Well, here's the rules we were just talking about. It's obvious when to break a bond. That's when the tail of the arrow is on a bond. And it's obvious when to form a pi bond. That's when the head is pointing to a bond. The tricky one is when do you form a sigma bond? We saw that was a little bit subtle, but I think we've made some good progress on that. You form a sigma bond when the arrowhead is pointing to an arrow which was not already sharing the electrons represented by the arrow. So it's a little bit longer to state, but I think we've made some progress on that. That's how you know when to break a bond, form a bond, or both. And then there's only one more thing to do for using electron-pushing arrows, which is change 2 charges. So to review, how many charges do we always change on every step of every mechanism?
2.
2. That's really crucial. You make the atom that's losing electrons at the start of the chain of arrows one step less negative, and you make the atom that's gaining electrons at the end of the chain of arrows one step more negative. We've seen it's an entirely mechanical process. There's no need to count lone pairs or count pi bonds to figure out the formal charge, or count bonds to figure out the charge. All you have to do is ask what formal charge did the atom start with, and is the atom gaining or losing electrons. Okay, so here in that handout, these are the rules that we were just going over. So these should be memorized. So I think a lot of students don't realize that there are rules for using electron-pushing arrows. They seem to think that they need to memorize the products of every step. But we don't need to memorize it. We can figure out the product by using these rules for the electron-pushing arrows. The most important rule, though, is maybe something I didn't write down. The most important rule is don't break any bond that the arrows don't tell you to break. Don't form any bond that the arrows don't tell you to form, and don't change any charge that the arrows don't tell you to change. So that might seem obvious, but the most important rule is don't make any changes that the arrows don't tell you to make. Okay. And do make all the changes the arrows do tell you to make. All right, so you can you have those rules there then in that handout. And notice that all the examples we've done so far have been fake, made-up examples. So obviously we weren't relying on our memory here, we were using the rules for electron-pushing arrows. So we can see that the rules really do allow us to draw the correct product. Now, so now we're going to stop using fake examples and start using some real examples. Okay, so our goal here is to draw the product. from this step using the rules we were just talking about. So I'll demonstrate what I think is the best way to attack this type of problem. The first thing that I'm going to emphasize is you should always number all your carbons.
Okay.
You should always number all the carbons. So I did that here. The next thing to do is to redraw one of the starting materials. So I'll redraw the larger starting material. Now, what numbers should I give to this molecule? Well, you want to give the same number to atoms that are the same in different pictures and different numbers to atoms that are different. So would you agree these are bad numbers? Do you see why these are bad numbers? Because they're not consistent with my earlier numbers. Instead, I should number this carbon 1. Why am I calling this 1? To show that it's the same as this carbon over here. And then what number should this be?
2.
And this one?
3.
Okay. So we're going to be numbering all the atoms in all of our pictures. By the way, the numbers are completely arbitrary, right? Would you agree that if we wanted to, these numbers are perfectly fine too? Now, what number should this carbon be?
2.
And this one?
1.
And this one?
3.
So these are not IUPAC naming numbers. If we were doing IUPAC naming, we'd have to go 1, 2, 3. These are what we could call reference numbers. They're just numbers for our own benefit to make sure we're drawing the product correctly, so we don't have to follow the IUPAC naming rules. Okay, so here's the process. Does this arrow tell us to form a bond, break a bond, or both?
We are only forming a bond.
Between which two atoms?
Between bromine and the carbon number 1.
So I've done that. I've formed that bond. Now, does this tell us to form a bond, break a bond, or both?
Break a bond. The bond that's broken is the sigma bond between carbon 1 and iodine.
So I can use my eraser to break that bond. We should always do these problems in pencil, always in pencil, so we can erase things. Okay, and that's it for the arrows. And there's only one more thing to do, which is change charges. How many charges do we always need to change on every step of every mechanism?
2.
So what's one of the atoms whose charges has to change here?
Bromine.
And what should be its new charge?
Neutral, or 0 charge.
Because it started negative and it lost electrons. And what's the other atom whose charge changed?
Iodine will become negative.
Because it started neutral and it gained electrons.
Yeah.
Great. How about carbon 1? Does its charge change?
No.
Because it's in the middle of the arrows. Good.
Okay.
Okay, so that's our first example of doing a real example with a real molecule. Those are the rules for electron-pushing arrows. Now, this is a pretty simple reaction that you might have already seen in the first semester. I don't know if you remember this reaction or not, but the point is it doesn't matter whether you remember it or not. Even if you've never seen this reaction before, we can use the arrows to draw the correct product. Once we're given the arrows, we can always draw the correct product, whether we've seen that reaction before or not. So the steps that I just went through, those are the steps I would recommend that you use on all of these problems. Start by redrawing one of the starting materials. Oftentimes it's better to start by redrawing the larger starting material. And then you use your pencil and eraser to draw new bonds and erase bonds. And you always have to remember to change 2 charges as well.
Okay.
Okay, so now it's your turn. So let's start practicing this again. So now let's start practicing this on your screen. So we can try these techniques on your screen. So try drawing this molecule on your screen and try showing what the product would be.
Okay. So we are going to form a bond.
And let's see, for the purposes of your notes, you should probably copy the starting materials first. Copy the starting materials onto your screen and the electron pushing arrow. Basically copy exactly what I have written here. And then off on the right, you can draw the product like you would on a real OChem problem.
Good.
All right, so remember the first thing to do is put in your numbers.
Oh, yeah.
Okay.
Okay, so we are going to form a bond there, and then we are going to break a bond there.
Okay, good. And let me just say something about how we can communicate with each other in the tutoring sessions. One thing I notice, so one thing that's important on these problems is as you go to always double check each step. Remember that sometimes the first thing you write down might be mistaken and you need to double check that. So you should always take your time as you're drawing each step and double check it. And I want you to have the time to do that. So every time, so we're going to be doing lots of practice problems together. So what I'd like you to do, if you can, is whenever you do a problem, you should tell me when you're done with the problem. I'm not just going to assume that you're done just because you stopped writing, because you might be thinking about it, or you might be double checking your answer. So going forward, when you're done with each problem, just go ahead and say, I'm done, or that's it, so that I know you're done checking and we're ready to move on. So done with this problem?
Yeah.
Excellent. And you got it right. Excellent. So that's correct. That is the correct answer. Very good. All right. So I'll write something else on my screen, but that's the exact right way to use those rules for electron pushing arrows. Very good. So I'll go back to my screen. Okay, so let's try this problem.
All right. Okay, so we are going to...
Remember to start by numbering all the carbons.
Thank you. Is that okay?
Including the carbon on the left.
Oh, okay. I'll just make that 5. Okay, so we are going to add this carbon number 5. And we're going to break the bond with the bromine. Yeah, I am done.
Yes, very good. Excellent. That's the way to do it. That's correct. Very good. That's a good application of what we talked about. So I'll just go back to my screen and write down another problem. But that was good.
Okay, thanks.
Let's try this problem.
Okay. Okay, we've got to number these. So that N is going to attach here. It's going to gain a positive. And that bond is going to break. Oops. Looks a little messy, sorry. But now I'm done.
Okay, that was actually very good. You might not seem like it, but almost all students get this wrong. You got this right, but almost all students get this wrong because hardly any students think to change the charge on the nitrogen to positive. That might not seem like a big thing, But the thing that you did that was very important here is that you changed the nitrogen into a positive charge. That was very important. Okay, so that's good that you did that. And the way you knew to do that was by using our rules for electron pushing arrows. So this is a reaction you probably don't remember too well from the first semester, but it doesn't matter whether you remember it or not. The arrows here tell us that the nitrogen started neutral and it's losing electrons, so it becomes positive. If we don't put that positive charge in, the rest of the problem would then become impossible for us. So that was really crucial that you put in that electron pushing arrow. All right, but that's right. So I'll go back to my screen.
Okay, thanks.
So now let's try drawing the product here.
Okay.
Take another look at my screen. I think you might have miscopied the problem by leaving out one of the arrows.
Oh, yes, I did. Thank you for catching
So that's
that.
important. We need to include all the
Right there.
arrows.
Thank you. Okay. So here, looks like this is going to combine, form a positive charge. That bond will break and it will gain lone pair and lose its positive charge. Yes, I'm done.
Okay, good. Well, you can see the crucial thing, we have to make sure that we pay attention to every single arrow. But once we got both arrows in there, you did draw that process correctly. Very good. So did the charge on the hydrogen change?
No, I did not.
Why not?
It was in the middle of
Yeah.
the chain of arrows.
That's right. So its charge did not change. Okay, that's right. Let's just keep going. So I'll go back to my screen and give you another problem.
Okay.
Let's try this problem.
Okay. Seven. Okay, looks like this carbon 6 have a new neighbor. Positive charge. One in this iodine. Okay, I'm done.
Okay, that was very good. Again, you avoided a mistake that most people get. This might have seemed straightforward, but most students get this wrong. So you did this correctly. Very good. I'm going to go back to my screen.
Okay.
How do most students get this wrong? Most students draw this. they do something like this. That is, they don't bring along carbons 1 and 2
Oh,
on a problem like this. A lot of students say, oh, this means I'm moving the nitrogen over onto this molecule. A lot of students say, oh, I'm moving the nitrogen to this molecule. And then they don't think about what happens to the 1 or the 2, or they write them off to the side.
I see.
Something like this. Okay, well, maybe I shouldn't even show you this because this is the wrong answer. But anyway, this is the thing to avoid. Do you see why this is wrong? What the students don't realize is that what they've done now is they've broken a bond. They broke the bond between 2 and the nitrogen. They probably didn't even think about it this way. Students just say, oh, I'm moving the nitrogen from here to here. But that would involve breaking this bond. But how do we know this bond should not break?
There's no arrow showing that it should break.
Yeah, there's no arrow telling us to break the bond. If there's no arrow telling you to break the bond, you can't break it. So 2 and 1, as you figured out, should actually get carried along for the ride. So you did that correctly. So notice this is why you should not think that this means, you shouldn't say to yourself, this means we're moving the nitrogen. We're not moving the nitrogen from this molecule to this molecule. Instead, you should just ask yourself, which bond should I form and which bond should I break and which 2 charges should I change? That's the way to avoid mistakes. If you think about moving an atom from one molecule to another, that can lead to mistakes. This doesn't mean we're moving the nitrogen from this molecule to this molecule. It means we're forming a bond between the nitrogen and carbon 6, so it carries along all the other bonds that it had before. Well, anyway, you did that correctly, so that's good. All right. Okay, let's try drawing the product here.
Okay. Okay, I'm done.
Okay. Now, how many charges should we change on every step of every mechanism?
Thank you. Yeah, I should have added a positive charge right there.
Okay, good. That's right. Yes. So to review, how many charges do we change on every step of every mechanism?
2.
2 charges. How do you know to change the charge on? So that's something I mentioned, that the reason I'd like you to tell me when you're done is because hopefully you're going to be taking a couple seconds to double check your work each time,
Sure.
just like you would if it was a math problem. But what should you be thinking about when you're double checking? Well, one thing you should always ask yourself is, did I change 2 charges? Because what's the most important factor in organic chemistry?
Charges.
So what's the most important part of this picture to get right?
The charges.
That's right. So what's the most important thing to double check?
The charges.
That's right. All right. I just repeat the same thing over and over because it just has to be reinforced. It's more important to get the charges right than even to get the bonds right. If we can't get the charges right, there's no way to figure out the next step of the mechanism. I think sometimes people will look at a problem like this where they leave out the charge and they'll say, oh, I did pretty good. At least I figured out most of the problem. I just left out that one detail of the charges. But we're trying to reorient our thinking. If we get one of the charges wrong, we've totally messed up the problem. Okay. All right. So that's what the purpose of this practice is, to avoid that. And again, you have to treat this like math. It's natural to make mistakes when you do math problems. The key is you have to always double check yourself to catch those mistakes. It's natural to be making mistakes on these OChem problems, but we have to treat it like math and make sure we're double checking to catch those mistakes, especially with the charges. Okay, so now we have that correct. So I'll go back to my screen. Try this problem.
All right. Okay, I'm done.
Good. So in this case, we were careful and we carefully changed 2 charges. So it's good that you did that. Very good. All right, I'll go back to my screen now.
Thanks.
So let's try this problem now.
Okay.
Remember to start by numbering all the carbons.
Thank you. Yeah, that's right. Okay, I'm done.
Okay, that's good. That was a good, careful process for working that out. Very good. Let's go back to my screen. Good. Also, that's a good use of the numbers here. So we called this 1, 2, 3, and 4. I think this molecule you called maybe 5, 6, and 7. You did something pretty important here. You didn't call this 5, 6, and 7. Why didn't you call this 5, 6, and 7? Because you'd already used up those numbers here. This carbon is not the same as this carbon, so it needs a new number. That might seem obvious, but it's important to be careful about that. You should only give the same number to carbons that are the same. These carbons are different from these and these, so they need new numbers. We give the same numbers to carbons that are the same, but we give different numbers to carbons that are different, and you did that correctly. Again, many students get this wrong. Many students think the answer is this. Many students think, oh, I should move the OH from this molecule to this molecule, but we now know this is a completely wrong way of thinking about it, because this would involve breaking the bond between 9 and the oxygen. We know we're not breaking this bond because there was no arrow to tell us to break it. So you avoided that mistake. That's good. The oxygen drags 8, 9, and 10 along with it.
Yeah.
All right, this example I'm going to demonstrate on my screen.
Oh, okay.
So I'm going to introduce a new idea here. Is this an ionic or a covalent bond?
That looks like a covalent bond.
How can you tell? Well, anything with a dash is always covalent.
Okay.
Anything with a dash is always covalent. So is this ionic or covalent?
Covalent.
Now, that doesn't mean that it's got to show a dash. Is this bond ionic or covalent between the carbon and the nitrogen?
covalent also.
How do you know? I didn't show any dashes. Well, basically, when there's a bond between two nonmetals, it's always covalent. Do you remember the nonmetals are from the right side of the periodic table? I think I sent you an email. Hopefully you have a periodic table close to you. The carbon and the nitrogen are both from the right side of the periodic table, so they're going to be forming a covalent bond, even though I didn't show the bond. I could have shown it. Now it's clear it's covalent because I drew the dashes. But even without drawing it, we know it's covalent because this is between two nonmetals.
Yeah.
Good. How about we could draw this in here. How about the bond between the carbon and the hydrogen here? Is that ionic or covalent?
It's also covalent because they are nonmetals.
That's right. That's a little bit confusing because hydrogen is on the left of the periodic table. But even though hydrogen is on the left of the periodic table, it's still a nonmetal. So this is covalent too. How about between the sodium and the carbon?
That would be ionic.
That's right. It's kind of clear here because I put in these charges. The charges here show it's ionic, but even if I hadn't drawn the charges, you should know it's ionic anyway, because where is sodium in the periodic table? On the left or the right?
The left.
The far left. Well, we
Yeah.
take something from the first column and a nonmetal, that's definitely an ionic bond. So even if I had not drawn the charges in for you, you should know that sodium and carbon is going to be an ionic bond because we're taking something from the far left with a nonmetal. So this is an ionic bond. Ionic bonds are dealt with differently than covalent bonds in organic chemistry. Ionic bonds are dealt with differently than covalent bonds. All the rules we've been talking about so far, I haven't been emphasizing it, but all the rules we've been talking about are rules for covalent bonds. We've been going over the rules for when to form and break covalent bonds. We haven't been talking about ionic bonds. Once it turns out ionic bonds are probably simpler. Let's see if I can find my example again. Here we go. Okay. So first of all, how can you recognize an ionic bond? Well, actually in OChem it's pretty simple. In organic chemistry, any bond between a nonmetal and sodium. What's another element from the first column of the periodic table besides sodium?
Lithium.
And what's another element from the first column besides lithium and sodium?
Potassium.
So any bond between a nonmetal and lithium, sodium, or potassium is covalent. Nope, is ionic.
Okay.
That will about cover it for OChem. You're not going to see too many other ionic bonds. That's about all we have to talk about right now. By the way, notice, again, hydrogen is in the first column, but it doesn't go in this list because hydrogen is different from lithium and sodium. It's actually a nonmetal as well. So hydrogen will form covalent bonds. But any bond between a nonmetal and one of these three elements. So you should memorize these three elements: lithium, sodium, and potassium. And we know any bond with them is ionic. In addition, so what would be the charge on lithium, sodium, or potassium then in an ionic bond?
The charge on lithium, sodium, or potassium would be a positive 1.
That's right, because they're in the first column, which means they want to lose one electron to get a complete octet, if you remember those ideas from general chemistry. Everything in the first column wants to lose one electron to get a complete octet. So they could always be drawn like this, with a positive charge. So lithium, sodium, and potassium are always what are called spectator ions.
Okay.
In OChem. I don't know if you remember that term spectator ions from general chemistry, but it means they're not going to participate in the reactions. Lithium, sodium, and potassium will never participate. Lithium, sodium, and potassium ions will never participate in the reaction in organic chemistry, which basically means we can kind of just ignore them. Lithium, sodium, and potassium will never participate in the reaction in organic chemistry. We can kind of basically just ignore them. So how would we draw the product in this case? Well, You break the bond with the iodine, form a bond with the CN, change 2 charges. And then what do we do with the sodium? Well, there's one thing that you definitely can't do. So remember, how is the sodium bonded to the carbon here? Covalently or ionically?
Ionically.
Would you agree it cannot be bonded to the carbon ionically anymore in this picture, though, because the carbon lost its charge? We haven't talked about this, but remember, ionic bonds mean a bond between charges, right? An ionic
Sure.
bond means a bond between charges. Well, since the carbon has lost its charge, there's no longer an ionic bond anymore between the sodium and the carbon.
Right.
So it would be wrong to put the sodium here. There's no reason to draw the sodium right next to the carbon anymore. There's no reason to draw the sodium right next to the carbon because they're not ionically bonded anymore. So one thing that you could do is you could just draw it off on its own now. You could just say, now the sodium is just off on its own, not ionically bonded to anything. Let me actually, so that's one, I kind of could have managed my space here a little bit better. So that's one thing you could draw. Or, so you could draw it like this. Or you could draw it like this. Since the iodine now has gained a charge, you could draw the sodium ionically bonded to the iodide now. Okay. Now they could be ionically bonded. Or, and here's what I think is best, the best thing is just don't draw the spectator ion.
Okay.
And this one, I think, is what's best. These are all correct. All of these are correct, but this is what's best. Because these are just spectator ions, because they're not participating in the reaction, why clutter up our picture with things that we don't need? So the best thing to do is just leave the spectator ions out. You can just go ahead and leave the spectator ions out of your product. They're not interesting to us in any way. They're never going to participate in the reaction. So why did I even bother mentioning these? I only mentioned these possibilities because you might see this sometimes in lecture or in your textbook. Your instructor might sometimes write it this way, or your textbook might write it this way, but for the student, this is the best thing to do. The best thing for the student is just don't draw the spectator ions. All right. Okay, so that would be my suggestion for Hale to handle that. Very good. Does that make any sense?
Yeah, that makes great sense.
All right, so now you should try this problem.
Oh, okay. All right. Break off. Okay.
Okay. What about the sodium?
I just chose not to draw it.
I think that's a good choice. Excellent. Good. So that's right. That was my advice. The sodium is just a spectator ion, so it's best just not to keep drawing it. Excellent. So that was the point. So it took a while to talk about it, but it's easy to implement that strategy. Just don't draw the spectator ions. Very good. I'll go back to my screen. Who are the other ions that we treat like spectator ions besides sodium?
Lithium and potassium.
Very good. Excellent. Let's try this problem.
Okay. Right. Okay, done.
Okay, well, this is the most complicated example that we've done yet, but you took your time, and I think you got all the pieces right, so that's good. Again, this is a reaction you saw in the first semester, but you might not remember it anymore. The point is, it doesn't matter whether you've ever seen this reaction before or not, there's rules for using electron-pushing arrows. If we just follow the rules, we can draw the product, whether we remember the reaction or not. And I think you used those rules correctly at each step. That's good. So this is, I think, the first example we've done now with 3 arrows. But you took your time, you did that correctly, and you left out the potassium. We talked about that as well. That's just a spectator ion, so the best thing is just to leave that out of our final product. Okay, well, you can't argue with success. That's right. So I'll go back to my screen. Good.
Great, thanks.
I don't remember if these are the same exact numbers you used, but I just wanted to point out again that you did a good job numbering here. So you did not do this. This would not be good because we already used those numbers over here. We don't want to use the same number for these carbons because they're not the same carbons. So you invented new numbers for these carbons. That was a good use of the numbers. By the way, why are we numbering all of the pictures? That might not seem obvious. It probably won't be obvious maybe for a couple of sessions, but it turns out people make far fewer mistakes when they number all the carbons. That numbering the carbons helps us to protect ourselves against lots and lots of mistakes. It'll probably not be clear early on how the numbering is helpful. It might seem like a pain, but it really pays off the more OChem you study. So we're just going to take our time and always number all the carbons in every picture. Now you might remember, if you remember from your class, I'll bet your instructor didn't number all the carbons. When your instructor was doing problems, I bet your instructor wasn't numbering all the carbons, but that's because numbering the carbons is a technique that's important for beginners. And your instructor is not a beginner. So, so after you've done 1 million of these problems, you might not need to number all the carbons anymore. And that's why your instructor isn't doing that. But for beginners, it's really important to always number all the carbons. And as we go, we'll see why that is. For right now, we'll just have to trust that. Okay, so we'll keep doing that. So let me go back to my screen here.
Okay.
Okay, let's draw the product here.
Okay. Okay.
Good. All right. We did an example like this earlier where we had forgotten to put the positive charge on carbon 2, but this time we got that correct. So that's good. I'll go back to my screen. And now let's try this problem.
Okay. Okay, I'm done.
All right. Okay, this was a little bit different from the examples that we did before, but you just have to take your time and follow the rules, and then you got that correct. So let's see. You changed 2 charges, and you did follow those rules. Okay, that's a little bit different, but you followed the rules and got that right. So let's go back to my screen, and I'll write down another example. Okay, let's try this example.
Okay. Okay. Done.
Okay, now that's very good. This problem is a little harder, a little bit different from any of the ones that we did before, but you just followed the rules and you still got the right answer to this. So this is what we might call a ring opening reaction. This is a ring opening. Do you see why I would call it that?
Sure.
Yeah. All right, but you didn't even have to know that term to get this right. You just followed the rules for the electron pushing arrows. One thing that you did that was good here is you drew your product in the same orientation as the starting material. That helps you to see that you've got this problem correct. So drawing the product in the same orientation as the starting material is a good way to get this problem correct. Excellent. I'll go back to my screen.
Okay.
What I mean is a lot of people would try to draw the product like this. Now, there's nothing wrong with this. This is also the right answer, but because it's not in the same orientation as the starting material, it's harder to tell that this is correct. So like what I'm saying is the way you did the problem is superior. The way you did this is superior because you drew the product in the same orientation as the starting material. And of course that happened naturally because you started by just recopying the starting material. So that's a good technique. That's what we could call the redraw and modify technique. Rather than trying to draw the product from scratch, it's better to start by just redrawing the original starting material and then using your eraser to modify it. And when you do that, you automatically get the product in the same orientation as the starting material. Okay, so I'm just saying the way you did that really is the best way to do it, rather than trying to straighten out the molecule necessarily. Good. All right. And let's try this problem.
Okay. Okay. Done.
Okay, very good. Again, this is a little bit different from the problems we've done before. I don't know whether you did or did not cover this reaction before, but it doesn't matter. If we just follow the rules, we can get the correct product here. This was another ring opening. It was just a smaller ring that we were opening in this case. So you did that correctly. Notice that the positive oxygen stays in the molecule. The positive oxygen stays in the molecule, just loses one of its bonds. All right, well, that was correct. You did that correctly. I'll go back to my screen. Okay, let's try this problem.
Okay. Okay, done.
Okay, point to the first arrow.
To the first arrow?
Yeah, sometimes I'm going to ask you to point to something just so that I know we're both talking about the same thing at the same time, since I can't point to your screen. Good. Does that arrow tell you to form a bond, break a bond, or both?
Both.
Good. Who are you forming the bond between? Or who did you form the bond between?
I formed it between carbon 3 and the hydrogen.
Excellent. Now, you didn't draw that in, but I guess your reasoning was that you didn't need to because you could treat that like a hidden hydrogen, and that's fine. That's a matter of choice. If you want to, you can draw that new bond, or you can just treat it like a hidden hydrogen and not draw the bond, as long as you're clear in your mind about what you're doing.
Okay.
If you were in doubt, if you were having trouble, it would probably be better to draw the bond. But if you're confident about the problem, you can leave that bond out.
Okay.
Now, here's the tricky thing. I'd say this arrow is just a little bit more ambiguous than the arrows before, because this arrow is, the tail of this arrow is not on an atom. The tail of this arrow is not on an atom, it's between two atoms. I think we talked about this difficulty a little bit earlier. So, it's a little bit ambiguous who we're forming the bond between. Should we form the bond between 2 and the hydrogen, or should we form it between 3 and the hydrogen? Well, really, it's just ambiguous. So what I've been trying to convince you of before, is that the arrows are usually not ambiguous. Usually the arrows tell you exactly what to do. You don't need to use any judgment. Usually the electron-pushing arrows are an excellent system, well designed, that tell you exactly what to do without using any judgment. But this is kind of the one exception, unfortunately. This is one part of the electron-pushing arrow system that's maybe not so well designed. This is the one way the arrows can be ambiguous. When the tail of the arrow is between two atoms, it can be ambiguous which of the two atoms is forming the new bond. So that's the next issue that we need to talk about. I think we've made some good progress. You've been doing very well on the examples I gave you so far. So we need to move to some harder problems where the arrows are a little bit more ambiguous. So here's what we're starting to do that. This arrow is a little bit more ambiguous. On the other hand, in this case, do you see it doesn't matter who you form the bond with. It doesn't matter whether you form the bond between 3 and the hydrogen or 2 and the hydrogen, because this molecule is symmetric. So those two carbons are really, in a sense, equivalent. If you had drawn the new bond between 2 and the hydrogen, then you would have put the positive charge on carbon 3, but that would really just be the same molecule as the one that you got. Does that make sense?
Sure.
Yeah. Okay. All right, so in this case, the arrow was ambiguous, but it didn't make any difference because it doesn't matter which atom is forming the new bond, because either way, we're going to get the same product. Now, so you decided that 3 was forming the bond with the hydrogen. That would mean that 2 is losing the electrons. That's why you put the positive charge on 2. Okay, so you did that correctly. Good. I'll go back to my screen. Okay, let's try this problem.
Okay. Okay.
Okay, good. All right, that's right. Now, why did you decide to put the positive charge on carbon 1 instead of on carbon 2?
Figured it was ambiguous. Either one would work.
That's right. Now, if you put the new hydrogen on 2, then you have to put the positive charge on 1. Or if you put the hydrogen on carbon 1, then you have to put the positive charge on carbon 2. But you don't need to worry about which one it is because these two carbons are equivalent. Because the molecule is symmetrical, either picture would give you the same answer. So you can just pick one and stick with it. So since you said that, so you had carbon 2 moving the electrons from one bond to another, it was carbon 1 that was losing the electrons. So it's the one that got the positive charge. Okay,
Right.
good. All right, I'll go back to my screen. Okay, so we're about out of time for today. So what would be our next job? Well, first of all, we want to finish learning these rules for electron-pushing arrows. We made a lot of good progress today. We've been getting these problems right. But we need to go on and figure out what to do when it does make a difference, which bond, when the two carbons are not equivalent, how do you know where to form the bond and where not to? So that would be a next topic for us to go over. How do you interpret these arrows when it does make a difference? Which of the two atoms is getting the positive charge and who is donating the electrons? So basically, the next job is to finish learning how to draw the product based on the electron-pushing arrows. And then after we have that down, what's the next job? Well, then the next job, obviously, is to learn how you can come up with the arrows on your own, right? Obviously, that's what's most important in organic chemistry. All of these problems I've given you so far, I've been giving you the arrows. All of these problems so far, I've written down the arrows for you, and all you had to do was just draw the product based on the arrows, and that's a very important skill. That's why we've been working on that. But then the next skill that's even more important is that in organic chemistry, usually you're not given the arrows. In organic chemistry, usually you have to figure out the arrows for yourself. And well, that's much harder. That will take up a lot of our time trying to figure out how you can figure out the right arrows on your own, but that would be the next topic for us to go over after we finish this one. Once we know how to draw the right product based on the arrows, the next thing to go over, which will take much more time for us, is learning how we can come up with the right arrows on our own. In a sense, that's what the whole OChem course is about. In a sense, the whole OChem course is about learning how you can draw the right arrows, but we can certainly start learning the general principles so that in many cases we can figure out the arrows on our own, even if we haven't seen the reaction before. So those would be the next topics coming up, but I think we made some progress on what we talked about here so far. Again, the point is there's really rules for electron-pushing arrows. So to remind you, what we've been practicing is these rules from the handout. So you need to memorize these rules. So we saw here we used the technique of first redrawing the starting materials. And then you use your eraser and your pencil to make changes in them. We've been numbering all the carbons in our before and after pictures. And then the rules are really quite simple. For every arrow, you either break a bond or you form a bond, or sometimes you do both. How do you know what to do? Well, here's the rules for whether you should break a bond or form a bond. And then most important, we have to remember to change two charges. And there's very simple rules for changing the charges. I should have been emphasizing, again, many students really overcomplicate that. For example, many students think that they need to count the bonds and count the lone pairs to figure out what the formal charge is on the atom. But we've been seeing that's completely unnecessary. You don't need to count the lone pairs. You don't need to count the bonds. All you need to do is ask, what charge did the atom start with, and is it gaining or losing electrons? If it's losing electrons, it always becomes one step less negative. And if it's gaining electrons, it always becomes one step more negative. So the point is, many students really overcomplicate drawing the product based on the arrows. I think they don't realize how simple these rules are. But I think we've been getting to the point where not only have you been getting these problems right, but you've been getting them right pretty quickly. So we've been seeing this is not the part of OChem that's supposed to require deep thought. There's some parts of OChem that require thought, but this is not the deep thought part of OChem. This is supposed to be fairly mechanical. Just like when you learn how to do long multiplication, it's not supposed to require deep thought. Once you've learned the rules for long multiplication, you're supposed to apply them pretty mechanically. Well, this part of OChem that we're going over here is not supposed to require deep thought. You can do it pretty mechanically, and I think that's what you have been doing. You've been applying the rules pretty mechanically and getting things correct. When we move on to the next topic, when we start trying to figure out how we can draw the arrows on our own, that's probably going to require some more thought. But this part of OChem is not supposed to require very much thought, even if it's a reaction you've never seen before. It's important for you to carefully review what we just went over today. I think we made good progress here today. You were getting almost all the problems correct, but my experience is that it's very easy for people to quickly forget stuff. So between now and Thursday, you want to carefully review this material, memorize the key ideas. You have to memorize change two charges on every step. You need to memorize the rules for when you're going to form a bond and when you're going to break a bond. Basically, what you should be doing is memorizing this section of the handout. This handout, make sure you have this handout handy during each of our next sessions. We will often be referring to this handout. By the way, you might notice there's many things on the handout that we haven't talked about yet. So for the time being, you should basically just ignore those. So for the time being, you can ignore the first page of the handout because we haven't talked about that. And then you can ignore the third page of the handout because we haven't talked about that. In fact, for the time being, the only part of the handout you need to worry about is the top of page 2. So far, the only part of the handout that we've talked about is here on the top of page 2. So those are the parts that you need to have memorized for our next session. And also, I think I'll probably be sending you a few homework problems. So you should definitely try to get those homework problems done before the next session. The key to OChem is practice. We need to make sure that these things are easy for us as we make the problems harder and move on to the next step. Remember that our goal is to start learning how we can draw the arrows on our own. Our goal is to start learning how we can draw the arrows on our own, but the only way you can do that is if this material is easy. This material has to be easy for us so that we can move on to the next step. It's like if you're playing chess. If you're playing chess, you have to know how the bishop moves and how the rook moves. And not only do you have to know that, that has to be easy for you. There's no way that you can learn the advanced elements of chess if you're still spending some time doubting yourself about how a bishop moves or how a rook moves. Well, this stuff is like how the pieces move in chess. This stuff has to be easy for us so that we can move on to the more complicated material.